Good afternoon. On behalf of the National Institute of Statistical Sciences, I would like to welcome our viewers from around the world. My name is Daniel Jeske, and I'm coming to you from the Department of Statistics at the University of California in Riverside. I'm delighted to be the moderator for what promises to be a very interesting webinar entitled Digging Deeper into P-Values, a follow-up with 3 authors. In 2017, the ASA released a statement on p-values that addressed their context and purpose. Since that time, many statisticians have been thinking and writing about alternatives to the traditional p-value. This work led to the publication of a special edition of the American Statistician that featured 43 papers related to the use of p-values. Earlier this year, NISS hosted a webinar discussing what some of those papers proposed as alternatives to the traditional use of p-values. Today, we are going to take the conversation on p-values a step further by presenting to you 3 distinguished authors who published in the special issue to share deeper insights about their specific ideas. I'm excited that our speakers are such big thinkers on the topic of p-values. Today, you will hear from Jim Berger from Duke University, Sander Greenland from UCLA, and Robert Matthews from Aston University. Our schedule today shows the lineup is Jim, Sander, and Robert. They'll each be speaking to you for 30 minutes. There might be time for a question right after they finish their prepared remarks. But then later in the webinar, our last half hour is dedicated to Q&A with our viewers and speakers. The logistics for today's webinar is that our hosts are Glenn Johnson and James Rosenberger, working in the studio at NISS, helping with the production of this webinar. The format for asking questions is as follows. The attendees, all our viewers, are view-only participants, but they can use the question and answer feature at the bottom of the Zoom window to write in questions at any time during the webinar. To do this, simply click on the Q&A icon at the bottom of the Zoom window, type in your question for the panelist and click enter. We'll be monitoring that window and preparing the questions for our speakers. Finally, when a speaker is sharing his or her screen, as I'm doing now, you can minimize the displays of the other speakers by clicking on this little dash in the upper left-hand corner of the panel of thumbnail photographs. If you do that, it'll minimize the speaker photographs and you'll have more room for the slides that they're displaying. So with that, it's my great pleasure to introduce our first speaker, Jim Berger. Jim is the Arts and Science Professor of Statistics at Duke University. His current research interests include Bayesian model uncertainty and uncertainty quantification for complex computer models. Jim has been the president of the Institute of Mathematical Statistics and also of the International Society for Bayesian Analysis. He was the co-editor for the Annals of Statistics and was a founding editor for the Journal of Uncertainty Quantification. Among his many distinguished achievements, Jim was elected to the National Academy of Sciences in 2003. Jim?
Yes. Let me... Okay. Okay, good, it's working. Great, well, thank you, Dan, for the introduction and for organizing this session, and thanks to NISS, Glenn and Jim for hosting this. Okay, my talk today is based on this paper that appeared in the American Statistician, and I'm pretty much just going through the paper. It was joint work with Dan Benjamin. The premise of this paper was that while misuse of p-values may gradually disappear, it's not going to be an immediate process. And so we need some fixes that can be done at various levels of sophistication, things that can be implemented right now to help improve the situation. So here were the 3 recommendations, and I'll be just mentioning them right now and then going through the justification, motivation, and background for them as we go through the talk. The first one is something that's been mentioned a lot, that statistical significance for a novel discovery should have, instead of a p-value threshold of 0.05, should have 0.005. With the idea being that if you publish a discovery with a p-value between 0.05 and 0.005, you'd use the word suggestive rather than significant. The second recommendation has to do with the notion that p-values are difficult to interpret. And so it's an attempt to convert a p-value into a more interpretable measure, namely the odds of one hypothesis to the other. So if we have an odds of H1 to H0 of 10 to 1, that means H1 is 10 times as likely to be true as H0. Now that's somewhat difficult to do, but there's an interesting bound, 1 over minus EP log P. So you just plug the p-value into this, you look at this bound, and you interpret this as a bound on the odds of H1 to H0. And then finally, recommendation 3 is meant to deal with this kind of exploding world of multiple testing, where it can be very important to determine and report your prior odds of H1 to H0. This is kind of 1 over minus EP log P would be what the data is saying. And then you have to say prior odds of H1 to H0, and then you report the product of the two as the final odds. So I'll be going through each of those 3 recommendations. First, however, let me just mention a little bit about the issue of misinterpretation of p-values. So take a simple test of theta equals 0 versus theta not 0 based on data arising from some density, f of x given theta. We have a test statistic t, the actual observation x, and the p-value. So the test statistic is one for which large values of t discredit the null hypothesis. So the p-value is just the probability that the random test statistic would exceed the observed value of the test statistic under the null hypothesis. Now the problem is that since p is a probability, and it's very easy and it's quite common for non-statisticians to interpret p as something like the probability that H0 is true given the data, or interpret 1 over p as the odds that H1 is true compared to H0. So for instance, if you ask many people what p of 0.05 means in terms of odds, they'll say that implies that H1 is 20 times more likely to be true than H0. This is not right. One version of the odds, and the version of odds that I like to work with most, is called the Bayes factor, but I'll just call it data-based odds today. And the data-based odds of H1 to H0 for a prior distribution pi of theta, I will be introducing prior distributions, but then we'll get rid of them shortly. Not that I want to get rid of them, but we just will. For a prior distribution pi of theta under H1, the data-based odds of the alternative hypothesis to the null is just the density of the data under the alternative hypothesis averaged out over the prior distribution on theta. And then the distribution of the data under the null hypothesis is just f of x given 0, because the null hypothesis is theta equals 0. And the fact is, this is virtually always much smaller than 1 over p. So for instance, where 1 over p is 20, this odds here will typically be something like 2 or 2.3. So instead of having 20 to 1 odds against the null hypothesis, one has more like 2 to 1 odds against the null hypothesis when you observe a p-value of 0.05. So that's the basic problem. And that I'm going to start with, I'm going to kind of work backwards because recommendation 1 follows from recommendation 2. So I'm going to start with recommendation 2, which is this idea of trying to convert a p-value into an odds statement. So the data-based odds of H1 being true to H0 being true are at most equal to 1 over minus EP log P. Okay, and the justification is robust Bayesian theory. A version of this was first done by Vladimir Volk in 1993. The version I'm talking about was in a paper that we had in the, I think it was in the American Statistician again in 2001. And it's based on the following theorem. If you have a proper p-value, by definition, you can show that under the null hypothesis, it has a uniform distribution. So we just considered testing that null under some alternative. Under the alternative, P will have some density G of P. Now we don't know what that density is, but it will be decreasing from 0, as you go from 0 to 1, it will be decreasing because small values of P tend to discredit the null hypothesis, and so they'll have larger density. Small values of P should have larger density under the alternative than under the null. And in fact, in this paper, we make an argument that a very good constraint on this density G that's very natural in many problems is to say that minus log P has a non-increasing failure rate. I won't go into that today, but if you want to see the justification, you can look in this paper. Well, so then the Bayes factor now, if under the null hypothesis, it's uniform, so the density is just 1. Under the alternative, P has this density G of P, so G of P divided by 1 is the odds in favor of the alternative hypothesis. And then it's just a math theorem that says that under this condition, this quantity is less than or equal to 1 over minus EP log P. So if, let's just look at a couple numbers. If P is 0.05, this bound is 2.4. So this says the odds of the alternative hypothesis to the null cannot be any bigger than 2.4. That's the most the data can possibly favor the null over any prior. If a p-value is 0.01, the odds are about 8. So the most that the data can favor the alternative hypothesis in terms of odds is 8 to 1. All right. Now, all of this is this is a simple bound, but there were initially concerns about this bound because when you compute Bayes factors using real priors, you get you find that the Bayes factor or the database odds will depend on the sample size n. And these bounds, this bound obviously does not depend on the sample size. It only depends on the p-value. Then I ran across some studies from John Ioannidis and others that shed some light on this. These studies looked at large collection of published papers where the p-value was between 0 and 0.05. For each of them, computed a Bayes factor also. So went back and somehow got the data or the sufficient statistics or something, and they computed a Bayes factor for each study. Now, instead of doing the Bayes factor of the alternative to the null, they did the Bayes factor of the null to the alternative, which is just the inverse. But that's what will be appearing in these graphs. And then they graph the Bayes factors versus the corresponding p-values. So there's 4 graphs. The first 2 are from 272 epi studies with 2 different choices of the prior. The third was for 50 significant meta-analyses, and the last one was for 314 ecological studies. So there's 3 epis and 1 ecological study. There are the 4. I'm just going to focus on this first one here, and so I blew it up so we can talk about it a little more. So this has to do with the risk factors in the epi study, but that's not relevant to us. What's relevant is each study here has a p-value between 0 and 0.05. So let's look at this study right here. That has a p-value of about 0.02, and the reciprocal of the Bayes factor, or the Bayes factor of the null to the alternative, is about 0.75, like 3 to 4. So it slightly favors the alternative hypothesis, but not very much. Okay, and that was where the p-value was 0.02. So here was the real Bayesian computation, and it says the odds are close to 1. So there's nothing much going on here. Now, what was and as you can see, this scale over here of the Bayes factors from 0 to 1. So all of these Bayes factors or database odds are much bigger than the p-values. What was interesting about this is we noticed that a lot of the Bayes factors were sort of concentrated near this lower boundary here. And what is that lower boundary? Well, it's essentially the database bound over B01 would be that B01, the Bayes factor of the null to the alternative, is bigger than minus EP log P. And that's what this dashed gray line is. So we were rather excited when we saw this because it seems like very often the real Bayes factors, when you compute them, are pretty close to minus EP log P. So that gave the notion that reporting minus EP log P would not be would be a useful idea. Again, it's a bound. So for this particular study, reporting minus EP log P would have been not so good because it would be saying 5-to-1 evidence. 0.2 is 5-to-1 evidence in favor of the alternative. So it would be saying 5-to-1 evidence in favor of the alternative when the true odds are only 4-to-3. So it's making a mistake, but it's making a big improvement over the misinterpretation of 0.02 as being 50-to-1 odds. It says 5-to-1. The real answer was 4-to-3, but still we've gone a long way in correcting the misinterpretation problem. And in all four of the other figures, you see again the minus EP log P. Here, again, a lot of them are very close to it. These two, not so much. But nevertheless, the bound is a useful bound and considerably improves over just reporting the p-value. So now where does recommendation 1 come from? Replacing 0.05 by 0.005. Well, from that table, the table right before it, 0.05 had a bound of 2.44 for the database odds. 0.005 had a bound of 13.9. So I don't think anybody views like 2.4 odds as being very compelling evidence. On the other hand, this is close to 14, and 14-to-1 odds in favor of H1 is reasonably strong evidence. So based on the bound on the database odds, we felt that reporting P at 0.005 as the level of significance is reasonable. Now, we're not the first to have done this. In fact, this has been mentioned many times. In fact, in 2018, in Nature Human Behavior, the article Redefining Statistical Significance argued precisely for this change. It had 72 authors. Here they were, leading scientists from a wide variety of disciplines, mostly well, there's statisticians, biostatisticians, epidemiologists, and then all the social sciences. I highlighted Dan Benjamin and Val Johnson. They were the main instigators of this and did the bulk of the work. Now, I'm not sure any of these people agreed as to the logic behind why they recommended going from 0.05 to 0.005, but they all agreed with that statement. It's impossible, as I think the ASA discovered, to get a collection of people to agree on what to do about the p-value problem. But this one, everyone could agree, okay, that's a step in the right direction. Then finally, recommendation 3 is to having the database odds is nice. But these days, we also have to worry a lot about prior odds. So we find the prior odds of H1 to H0, and then you find the posterior odds by essentially using Bayes' theorem. So here's Bayes' theorem stated this way: if we have we have the prior probability of H1 and the prior probability of H0, then a form of Bayes' theorem says that the posterior odds, so probability of H1 given X is the posterior probability of H1 given the data. And so the ratio of that to the posterior probability of H0 given the data is the posterior odds. And a form of Bayes' theorem says you get that by multiplying the prior odds times the database odds or Bayes factor. If you want to use the bound, the robust Bayesian bound would say the posterior odds cannot be any bigger than the prior odds times 1 over minus EP log P. So here we're going to be focusing on that prior odds. So here's a typical example of today's testing world. This is genome-wide association studies. So in GWAS studies, things go on like this. There's testing the null hypothesis that some gene is not associated with disease D. versus the alternative that the gene is associated with disease D. So this has been going on for something like 13 years, these kinds of studies. And the early studies, up until about 2007, for the first like 10 years of research, almost universally failed to replicate, with estimates of replication rate as low as 1%. And the reason is because they were doing extreme multiple testing at not extreme p-values. They were saying, oh, I got a p-value of 0.001, that's small. I will claim an association between that gene and that disease. But the trouble is they were testing 1 million genes versus 20 diseases, and so they were doing 20 million tests and not properly adjusting for the multiple testing. So in 2007, a couple of papers appeared that brought this to the fore, that there was a severe problem. One of them appeared in Nature, and it proposed a p-value cutoff to declare a discovery, to declare an association. The p-value had to be less than 5 times 10 to the minus 7th. I think today for these things, it's something like p less than 10 to the minus 10th or something, because there's more and more multiple testing done. They found 21 genome disease associations, 20 of which have been replicated. And the key part of their analysis is they said, we have to judge what the prior odds of the alternative hypothesis to the null are. And they judged them to be 1 to 100,000. They said, that's the odds that any particular random gene would be associated with a particular disease. So this was obviously done by the scientists who knew a lot about genetics and diseases and things like that. They said this could be off by a factor of 10, but nevertheless, this was the assessment they made. Now, the data-based odds for their 21 claimed associations ranged from 10 to the 4th, so that's 10 to the 4th to 10 to the 73rd. Now, it seems like large odds. Odds of 10,000 to 1 seems pretty convincing, but that one isn't. To take the data-based odds, to get posterior odds, you have to multiply the data-based odds by the prior odds, and when you multiply 10 to the 4th by 1 over 100,000, you get 1/10. For this one, this is indeed overwhelming evidence, 10 to the 6/8 odds in favor of the alternative. But so curiously, for this one, the odds are 1 to 10. So the odds are 10 times in favor of the alternative after you adjust the data-based odds by the prior-based odds. This, incidentally, was the one that hasn't replicated. And that's because when you do the analysis, it suggests no, there's reasonably strong evidence in favor of the null hypothesis of no association. All right, so that's a sort of a justification for the three suggestions, recommendations, and some caveats about it. Well, the bound on the data-based odds only applies if H0 is a plausible nested precise hypothesis. So a nested hypothesis is one in which at least one of the unknown parameters in H1 is specified. The simple version we considered earlier was just theta equals 0 versus theta not 0. A plausible hypothesis is one that has non-zero prior probability. If the null hypothesis is implausible, one shouldn't even be doing a test to start with. Notice that often the null hypotheses have extremely high probability. In the GWAS example, the prior probability of H0 was like 1 minus 10 to, oh, sorry, it's 1 minus 10 to the minus 5, sorry. We can't have a negative probability, can we? I have to say that we felt somewhat guilty about recommendation 1. I mean, does it really, I think it really does improve the world if we replace the 0.05 cutoff by the 0.005 cutoff. But, lots of people correctly argue against having a particular cutoff. Sometimes I think a cutoff is a good idea if it's chosen scientifically. So in the GWAS example, they thought hard about everything, and they decided to choose an odds cutoff of 10 to 1 for a true discovery to a false discovery. And I presume they based that on an analysis comparing the costs of a false positive and the cost of a false negative. And then they judged that in all of their GWAS tests, they wanted 10 to 1 odds of a true discovery to a false discovery. I don't see anything wrong with that. If a cutoff is set up based on essentially a scientific decision analysis, to me, that's perfectly fine. It just simplifies things for the scientists in the future. Also in our defense, note that the Bayes factor bound is not a cutoff. We do not propose using that in the cutoff sense. We think odds are easy enough just to talk about themselves. If it's 10 to 1, you know what's going on. If it's 1 to 10, you know what's going on. You don't really need a cutoff when you're using the Bayes factor bound. And then, of course, there's all the other things associated, the other problems associated with current significance testing. Maybe effect sizes aren't taken into account and things like that. And we certainly agree that those things have to be taken into account. Sometimes some people don't like Bayes. It turns out, however, that the reporting of these data-based odds, B10, has a complete frequentist justification. I'm going to do this a little quickly because I'm running short on time here and want to say something. If we consider Neyman-Pearson testing with a fixed rejection region R, you have a probability of type 1 error, alpha, and you have a power, 1 minus beta theta. And here's an interesting little lemma. It says that if you take the expectation of the Bayes factor under the null hypothesis over the rejection region, so you're averaging the Bayes factor over the rejection region, you get 1 minus beta bar over alpha, where 1 minus beta bar is the average power of the test with respect to some prior or weight function pi of theta, and alpha is the type 1 error. So this is what they actually did in the GWAS study. They said they wanted power over alpha to be, well, here, let me just say that here. In the GWAS study, they wanted an experiment with pre-experimental odds of 10 to 1. They had average power of 0.5. They had alpha of, they're solving for alpha. And they had the prior odds of 1 to 100,000. So they solved this equation. And then they got alpha of, has to be 5 times 10 to the minus 7th. So the point here, though, is that they did that because they thought of this as a valid frequentist report, the average power over alpha. But this data-based odds is equally as valid a frequentist report because of the fact that its average is these frequentist answers. So it is fully frequentist. Okay, I think I have 2 minutes left, but just I'm leaving several minutes for questions. So let me just conclusions and say a few things about the impact on scientific culture. So again, I think optimal is to report posterior odds times data-based odds, and incorporation of this, and especially in the multiple testing environments, is really needed. If you're just doing a single test, I don't know. I mean, whether one wants to put prior odds in there or not, it's less important. Oops. If you can't come up with prior odds, at least just report the data-based odds. If the data-based odds are unavailable, report the prior odds times the bound on the Bayes factor. If they're both unavailable, at least report the bound on the Bayes factor. And finally, if you can't do any of that, at least use a cutoff of 0.005. So this is kind of going from optimal to worst, but still something that is a significant improvement. I was giving this in a talk in a lecture this term, and in the class, one of the students was she was a political scientist, and when I was kind of like saying stuff like change the cutoff to be 0.05, she said, "We can't do that. That would, nobody would be able to publish papers anymore. Nobody would get tenure. All of science would radically change. How do you expect us to do that?" And my response was no, you don't have to change that culture. You could still say p less than or equal to 0.05 is the basis for publication. In fact, a lot of the argument about the reproducibility of science is that there's not enough suggestive reports being published. And so all of these p less than or equal to 0.05 reports should still be published, but they would just be labeled as suggestive, not significant. And the final comment I would make is that we're not thinking here with these recommendations of immediately changing scientific culture. We're thinking of them as providing a better way to communicate the strength of findings. So you can still have a paper that reports the p-value, but it also reports -1/- EP log p. And then people have a much better idea as to what is the evidence from that study. So thank you.
Thank you very much for that, Jim. We do have a couple minutes, and one of the viewers wrote in and was interested in your comments about how the proposal to change the threshold might impact multiple testing procedures in terms of 0.05 or 0.005.
Yes, yeah, great question. And that part of the suggestion is not really aiming at multiple testing. The part of this, it was suggestion 3 that was aimed at multiple testing, where sort of in Bayesian analysis, multiple testing is controlled through the prior probabilities of the hypothesis. So like in the GWAS study, they proposed that prior odds should be 1 to 100,000. So recommendation 3 is addressing the multiple testing issue, and the change of the threshold really has nothing to do with that.
Okay. And also, the bound that you talked about could be used to get a lower bound, I think, on the probability of the null hypothesis given the data.
Yes.
I've seen it described that way in your work.
Yeah.
And sometimes when I've mentioned that to people, they've asked me if there's any way to get an upper bound on the probability of H0 given the data.
Yeah, another nice question, but unfortunately the answer is no.
Okay.
The upper bound, okay, I mean the upper bound is always degenerate in the sense that you can always you can always choose a prior that in fact if you just one of the unfortunately common things that happens in Bayesian analysis is sometimes people just choose a vague proper prior, and one of the facts is that if you just let that vague proper prior be vaguer and vaguer, then the Bayesian analysis is going to say the null hypothesis is true. Mm-hmm. So there's never a way to get a bound on that side.
Okay. All right. Well, at least we have a clear answer to that question. Well, thank you very much, Jim. I'm going to move on now to the second speaker. We can come back to further questions for Jim in our Q&A session. So it's my great pleasure to introduce Sander Greenland as our second speaker. Sander is an emeritus professor of epidemiology and statistics at UCLA. He's a fellow of the American Statistical Association and the Royal Statistical Society, and a leading contributor to epidemiologic methodology, with a focus on delineating and preventing the misuse of statistical methods in observational studies. He's published over 400 articles and book chapters in epidemiology and statistics, and given a nearly uncountable number of invited lectures, seminars, and courses. We're so pleased that he's here for one more today. And Sander, please begin.
Thanks, Dan, for having me. And I want to point out that the actual title of my talk is different than from what was listed. I decided to go with this title that I've used before, because this is really what my talk's about. And I'm much more of a critic of statistics, and especially as it's evolved to the present. The last presentation by Jim Berger is an example exemplifies both the strengths and weaknesses of what I see in modern statistics. On the one hand, it presents a very carefully tailored tool for a particular kind of problem that was very well described by the GWAS example. And on the other hand, it attempts to generalize from that special problem to the whole world at large of science. And by going, for example, talking about going from a standard of 0.05 to 0.005, as if that's universally applicable. And that's absurd. It's like, would be like having a speed limit of 40 miles an hour universally throughout the country, even school zones and on superhighways and everything. And he did not mention that following his article with over 70 authors, recommending this change, there followed an article by over 80 authors saying that, no, we need to set alpha levels. If you're going to use these kinds of methods, we need to set them based on the context. You need to justify the alpha level you're using in any particular application. So it is a very good example showing the strengths and weaknesses of statistics as has been taught to now. That I see statistics as needing cognitive science and causality theory in its foundation and practice. So I want to the audience to understand that there are many people who agree with my radical stance that, at least in certain topic areas, they don't agree with me on their particular view of it or their solutions, but they agree that statistics is the sick man of science. It's really a technology, in my view, which is supposed to serve science, and it's served some areas very well, and it's served other areas very poorly. But here's a quote from somebody as uninhibited as I in criticism, Taleb, and see what he says. I don't have to repeat it. I do want to say that what he is saying is true of much of health and medical sciences, and that should really scare you every time you go to a doctor, every time you need medical care, because statistics has been a major contributor to the very poor practice of medicine. So what if the major problem here is not the users? I noticed that the big theoreticians, they always say, I teach it right, let's blame the user. To me, it's almost like blaming the victims, and the users are victims of the system, as are the consumers. What if the major source of the problem are the pundits of statistics and meta-research, who are neglecting their own cognitive deficiencies and those of the developers of statistics, the instructors, the users, as well as the consumers? So, in fact, I've heard for 30 years now, I've heard some people call statistical science an oxymoron. In the US, statistical training degenerated heavily into statistical mathematics, at least at the highest level, and computing, so that it just reduced to a ritualized form of machine learning. It treated context, meaning, and values as if those were mere abstract algorithmic inputs. We just saw that in the previous lecture with the use of prior distributions. Priors are mentioned. It's never mentioned exactly what the priors are involved. There is a condition that's placed in there about a monotonic, non-decreasing hazard and so forth, non-increasing, I mean, and so on. It's sometimes some of the assumptions that are inserted here make a huge difference in a particular context. And the idea that, so again, the idea is that these are universal conclusions is pernicious. The idea of abstract loss functions, when we have to talk about real losses and real prejudices, can be misleading. And this statistical science denigrated semantics, terminology, clear ordinary language, favoring instead deceptive, almost salesman-like jargon, like significance and confidence. And this degeneration of the science into a mathematical shell left behind explication and training and these essential components of scientific inference. How causal networks, not probabilities, produce data, inferences, and decisions. How cognitive biases as well as procedural problems enter into those causal networks, and how values, that includes personal values, motivations, goals, real costs and benefits, those determine cognitive biases and are implicit in all statistical methods, including the ones that we just saw. In that, there is a bias, value towards the null. Now, here's an empirical fact that is seems to be unpopular to mention, and I believe that the best of cognitive science has established this fact that we are all stupid. Me, number one, you can just ask many people. I'm sure they'll agree. We're all stupid. That's the human condition. That's why we're functioning here as a group, to try and upgrade a bit. Look at the real originator leaders of cognitive fields. Emil Tversky, my colleagues, they study artificial intelligence. Me, I study natural stupidity. We need to study that. We need to study intensely all the misuse of statistics and ask, where are we going wrong in the fundamental theory that leads to this kind of vast misuse? In fact, we just saw an example where Jim Berger said we could retain the 0.05 for publication. That means retaining the publication bias that it produces. That publication bias basing publication on a cutoff has destroyed whole areas of the literature. It's created mass distortions. What we need to see is the entire evidence. We need to base publication decisions on the quality of the execution of the study, not its outcomes. And that, to me, is a basic lesson of statistics. And yet we just saw encouragement to continue in what is a damaging mode. But this shouldn't be surprising, given that whenever there's a simple error that most laymen fall for, there is always a slightly more sophisticated version of the same problem that experts fall for. And it's frightening to think that you might not know something, but more frightening to think that by and large, the world is run by people who have faith that they know exactly what's going on. And that's equally true of the worlds of scientific research and statistics. The confidence people have in their beliefs is not a measure of the quality of evidence, but of the coherence of the story the mind has managed to construct. That's from Daniel Kahneman, Econ Nobel Prize winner. This typifies the fear some people have, justifiably, of Bayesian methodology, such as the type we've just seen. It emphasizes coherence over the quality of the evidence that's being plugged into those formulas. Few pushing reform have tested their ideas by comparing practice impacts. Now, we just saw an example where he did do that, and that deserves kudos. It worked very well in the situation that it was tailored for. And that's a sign of excellent statistical craft. But as confidence intervals illustrate, unintended adverse effects can be severe, just like with medicines. Bayesian methods open statistics to even more abuse via prior spikes and elicited priors. Those elicited priors are often just summary expressions of biases, literature misreadings, and personal prejudices. Here's more Kahneman. People assign a much higher probability to the truth of their opinions than is warranted. That, to me, is an example, a warning for Bayesian statistics. We can be blind to the obvious, and we are also blind to our blindnesses. And most relevant to statistics and soft sciences, like medical and social sciences, illusions of validity and skill are supported by a powerful professional culture. We know that people can maintain an unshakable faith in any proposition, however absurd, when they are sustained by a community of like-minded believers. For example, claiming that the probability of a point null is 0.5 is indifference. It can only be indifference under a very specific setting in which the alternative is something else entirely than what I would consider in the many applications. Here's sufficiency number one to address. It's really three items that I'll give as examples of the need for cognitive science and statistics to address human psychology and its biases. Nullism, which we just saw in a form, confusion of our need for parsimony or shrinkage with reality. We have a need for simplification, nature does not. Dichotomania, confusion of our need for summarization, simplification, and decision-making, as they had to do in the GWAS studies, with our preference for black or white thinking. Just because we make a decision, and Neyman emphasized this point, doesn't mean we have to believe it's the right thing or believe more. We just say, this seems to be our best bet. And then reification, confusion of formal models for reasoning, inference, and decision, whether they're frequentist or Bayesian, with real-world reasoning, inference, and decision. Nullism has a long and glorious history among physics idolaters, as in the form of pseudo-skepticism. There's a Wikipedia article on that topic. That's empirically indefensible certainty about nulls. Or Kelvin, whenever you see the Kelvin temperature scale, remember that he said right up to 1902, heavier than air flying machines are impossible. Continental drift is out of the question. That was said by Sir Harold Jeffreys, who is the hero of much of the current Bayesians. He's a geophysicist, lauded and accomplished, and he's also the originator of spike priors, which are formalized overconfidence. And see also Fisher arguing against cigarettes causing lung cancer, despite extensive evidence. There's an attempt to be revisionist about the history of Fisher, that the evidence wasn't that strong. Nobody who wanted to avoid lung cancer in life would have continued smoking any cigarettes had they seen the evidence at the time. Fisher came out challenging that relationship. Against nullism, reality is under no obligation to behave simply for you. Against dichotomania, Many, if not most important decisions are or should not be binary. Where do you set your oven, your thermostat, your medication level? Often medically, we're forced into binary decisions about our medication levels, which can be very destructive to many patients who are often seriously overdosed. And that's not their fault. It's the fault, in the end, of the pharmaceutical distributor, the medical system that tries to oversimplify things down. Maybe they'll get it down to 3 doses or 4 doses, and then that's better. Hidden reification. Researchers routinely publish inferences that ignore vast model uncertainties. They don't know a rationale for neglecting all the missing effects in their models. They just don't think about them. Many other cognitive biases contribute to design, analysis, reporting, and publication biases. And all of the ones on this list should be part of our training, but I don't have time to go over them. But these kinds of problems are the major reasons that most published research findings are false. These are problems that confidence intervals have turned out to perpetuate, unfortunately, unexpectedly. Here's a typical example. And you see this all the time. There are people say, oh, this kind of thing must be rare. All you have to do is open a medical journal and find it all over the place, where they find a 60% increase. This is just an association, not necessarily causation, but a 60% increase in autism spectrum disorder among children exposed to these antidepressants during pregnancy, at least as measured. And that is, in fact, look at the confidence interval. It's from about 1 to 2.6. That is completely consistent with previous studies, a meta-analysis that they cite that found a 70% increase. And look at that confidence interval. And yet the article concludes exposure was not associated with autism spectrum disorder. Despite all that, this is nullism at its worst. But people want to blame p-values for that. They want to blame testing for that. Here's an ugly fact. The main problems of p-values will extend to any statistics because they are caused by truth-subverting, perverse incentives, and cognitive biases, not by p-values. And the perverse incentives are the ones that create cognitive biases, wishful thinking, positive projection, to see what the incentives dictate. These biases pervade reports in fields like medicine. And some of the incentives are often to report ambiguous results as null results, as we just saw, as when the researchers want to explain away unwanted associations. In the last case, several of those researchers, we were pretty sure, had prescribed antidepressants during pregnancy. This is example, all that is example of value bias, and that pervades received statistical methodology, most often in the form of nullism. I'm going to rush through these in the time. This bias affects a good portion of the Bayesian literature, as I mentioned, where null spikes are used to represent a belief that a parameter differs negligibly from the null, as if it's been established what's negligible. They should be using interval tests in those cases where they do establish that. In most medical research settings, concentration of prior probability around the null has no basis in genuine evidence. In fact, prior spikes usually contradict genuine prior information. For example, medicines are pursued precisely because they affect physiological systems. That's the reason we study them. Still, many statisticians exhibit quite a bit of prejudice in favor of the null based on faith in oversimplified biological models. Nullism also arises from confusion of decision rules with evidence summaries and from adoption of simplicity or parsimony as a metaphysical principle instead of a heuristic. We might be confident that any effect present is small enough so that the cost of ignoring it is acceptable, but that's a value judgment. Note in the GWAS example, there was a statement about what replicated by some replication criteria, which could be debated, but there was no comment about the false negatives. Clearly, there must have been a lot of them, given the vastness of that family they were looking at, but there's no estimate there of how many were missed. Clearly, it wasn't thought that it was that important if they missed some. That's fine, as long as they state that. Statistical rules can worsen bad practices because the theory assumes we will use only perfect interpretations of carefully controlled experiments with a clear view of error cost. But most statistical analyses and soft science research are about applying decision rules to statistical outputs based on accepted defaults whose value-laden nature is not understood by users and readers. For example, as we just saw, misinterpreting p greater than 0.05 as no association. And the literature is god-awful. The literature encourages subtle, fallacious descriptions that are equivalent to treating p-values as if they were hypothesis probabilities. That's p-inversion. The literature is full of inversions like defining p as the probability that the results are due to chance, or nonsense like p is the probability of a chance finding. These are, at best, Bayesian probabilities. Many descriptions of the confidence intervals are actually defining posterior intervals. And 95% confidence intervals typically get treated as nothing more than 5% levels. Here's an example from a popular medical statistics made easy. The probability of any observed differences having happened by chance. That's what the p-value is supposed to be. Well, if the tested model, the null, is correct, what's the probability that a non-zero difference happened by chance alone? The answer is 100%. So I can only assume medical statistics made easy is code for made wrong. And all these problems underscore the need for coverage of reasoning errors and cognitive bias as an essential component of any specialty claiming to promote sound statistical inference, sound scientific inference from data. Instead, statistics programmers indulge in the ludic fallacy of treating all uncertainty as if it arises from games of chance. Random draws from a distribution of known form, instead of addressing our deep uncertainty about the form and sources of variation and bias. And what is inference? Here's a dictionary example, a conclusion reached on the basis of evidence and reasoning. Scientific inference is a complex and narrowly moderated judgment about reality based on an assumption that there's a logically coherent, objective reality that causes our perceptions according to discoverable laws. My perception and your perception are affected by the same things, and we want to find out what those are. Contrast scientific inference to statistical inference, which in all formalisms, whether they're Bayes or frequentists that I see in advanced textbooks, has become taking output from a data processing program and a learning algorithm and generating conclusions via decontextualized rules, formulas, with no meaning attached to them from a real context, as in the example I gave before. It converts oversimplified models of the mechanisms generating the data, the causes of the data, into abstract probability distributions instead. And it leaves a void in meaning that is a major contributory cause of inferential errors. So the challenge here is that statistics, like medicine, is a technology that has become a major source of harms as well as benefits. Successes have distracted and are used to distract the field from its failures. Mathematics has distracted attention from hard real-world problems, diverting research and teaching to math that solves nothing real if human cognitive problems are not addressed. Example, competence and integrity are widely compromised, yet are the core assumptions of almost all statistical methods. So it's time to face the ubiquity of error at all levels. Error is inevitable, not only in data and inference, but also conceptual missteps extending to the highest authorities. A key to minimizing conceptual error is to vary perspectives and consider a lengthy list of cognitive biases and claims. Why are they making this claim? A key to minimizing average error cost is uncertainty assessment to encourage well-balanced hedging. Full analysis of alternatives to accepted hypotheses or null hypotheses. So what are my recommendations to reconstruct statistics? Here's a simple start. Stop perpetuating the mistakes of great men of statistics and the cognitive bias they reflect. Create and encourage. That statistics education has assumed a sophistication of users, especially in mathematics, that's high enough to see through terminology to the correct general meaning. And perhaps that was true when Fisher taught. It became utterly false in the research explosion after World War II, when the pool of researchers exploded. Typical users now depend on words because the mathematics is for them simply symbolic incantations they must take on faith to get funded and published. My complaint here gets dismissed as that's just semantics. That is irresponsible because it fails to grasp the essential analogical information conveyed by the semantics, the meaning of the words in their context. That failure is common among the mathematically able who place syntax and deduction above these analogical processes, or even dismiss or miss entirely the role of analogy in mapping reality to math. Overthrow misleading traditional jargon and realign statistical terminology with ordinary language. Replace significance, a dinosaur from the 1880s, and confidence, Neyman from Neyman in the 1930s with compatibility, where the P varies from 0, no compatibility, 1 to full compatibility of data with the model used to compute the p-value. Well, here's something, get rid of Neyman's confidence trick. Assigning high confidence is not distinct from assigning high probability. This was pointed out by Arthur Bowley, a Bayesian statistician, when Neyman introduced confidence intervals in the JRSS discussion following his paper. So the idea is to rename and reconceptualize CI as compatibility intervals showing parameter values found in highly or moderately compatible with the data. This involves no computation or numeric change. It's all about perception. Compatible is unambitious and far more cautious than confidence. There's always an infinitude of models compatible with our data, and most are unimagined or even unimaginable given current knowledge. Just recall Jeffrey's error about continental drift. Confidence implies belief, encouraging the inversion fallacies that infiltrate discourse about the models, whereas compatibility is no basis for confidence. Here's an example of a hypothesis that's was compatible with the data up to a point. It was effective and it was false. Causal stories are what map hypotheses to data. Compatible but false stories may lead to effective interventions. Example, that malaria is caused by bad air. The name malaria collects near the ground around swamps. The implied effective solutions, raised dwellings and drained swamps. They were used for long before people discovered what we now know as the actual cause of mosquitoes. And they worked. But confidence in the story will eventually mislead. It could lead to silly interventions if you push the story too far, if you're too confident. Stop repeating Fisher's error of using null hypothesis for any test hypothesis, which openly invites nullistic bias. That contradicts null as in every credible English dictionary I've seen, the Oxford Dictionary, Merriam-Webster. They all say null has to do with the value 0. Instead, it used Neyman's term. Neyman recognizes the problem, and he used the term tested or test hypothesis and emphasized testing directional hypotheses, non-null hypotheses, and interval hypotheses instead of point null hypotheses. Stop repeating the massive error of not treating p-values as estimation tools, which also invites nullistic bias. Edwin James, a Bayesian of sort, pointed out that this distinction between estimation and testing is artificial and can really cause problems. Indeed, the distinction has been entirely destructive in encouraging tests and decisions to focus on just one point or model an entire spectrum of hypotheses and models, as in the Bayes factor analysis that Berger gave. Here's an example of plotting the entire p-value function in the first panel, the s-value function in the second panel, the likelihood function in the third panel, and the deviance function, twice the log likelihood, minus log likelihood in the other panel. And you can see the different impression it creates now with the Brown data, where the value 1 can be seen, no matter how you look at this, off to the side of where the data are most compatible, the models that the data are most compatible with. If you were publishing an article like Brown and I'll publish, this would be the honest way to report things, what their data, under their model showed. Shift emphasis away from conditional hypothesis testing interpretations to unconditional descriptive interpretations. The norm is the p-values, the probability statistic as or more extreme under the test hypotheses. That leaves background assumptions implicit. Use instead p-values the percentile under the tested model at which the statistic falls. The model includes the test hypothesis and all other assumptions used to compute p. The idea is that p-values don't test hypotheses, they test models. And here's a figure that was attempting to illustrate that. The traditional interpretation on the left, where we deduce a p-value, confidence intervals, and then we use those only to test the test hypothesis, when in fact, those are actually testing the entire set of assumptions of which the test hypothesis is usually just a small part. Stop using distortive inverse exponential scale of p-values for gauging evidence. Switch to the Shannon information against the model supplied by the test, the surprisable, or S-value. That is a simple transform, minus log p, it even cropped up in the last talk. It's a measure of data incompatibility with the model. It's an equal interval scale that's additive over independent test statistics, as Fisher used ages ago. This idea goes way back and has appeared many times since. This S value is hard to confuse with a Bayesian probability because its range is way above 1. It does not require a prior distribution, unlike Bayes factors, but can use a prior by computing P as a test of fit of the compound sampling model, random effects model. Now I'll skip through this other stuff since I'm out of time, right? And the overall idea is to stop and ask, what exactly is the entire set of assumptions being checked by the test? When all those test assumptions are made explicit on the table, you can then ask, how much information does the test convey against the entire model? This is an analysis for discovery, for refutation of absence of model violations. They do not, p-values and s-values do not provide confirmation. They do not provide evidence of absence of violations. That requires checking alternative models, as in a graph like this of the s-value from the Brown data, showing that there are many alternatives showing an association that are much more compatible with the data than the null value. So this is my closing slide, as in closing remarks, and I can save that for the end if I'm out of time here.
Okay. All right. Great. So thanks for those comments, Sandra. As much as anybody else, I like hearing comments that make me think about what I believe myself. It's either going to open up my horizons to some new ways of looking at it, or perhaps reinforce what I think. So you said some things that I found really interesting. One I wanted to just ask you about in particular at this point, which was that you said many, if not all or most important decisions should not be binary. And I'm just wondering, it seems like our world forces binary decisions. We have to decide if we're going to vote for candidate A or not. We have to decide if we're going to buy this car or not. And more perhaps pertinent to our discussion today, we have to decide if we're going to develop a new treatment to try and treat a disease, yes or no. We can't do it halfway. So I'm just wondering if you could clarify how, in a sort of an inherently binary world, how do we function with that premise that you made there?
I don't see the world that way. I mean, I find it, I'm trying to be really honest here. I find it astonishing that you would be thinking in those terms. Say I go buy a car. I go out there, there are so many cars competing for my attention, so many makes, so many models, so many options. It's not a binary decision. Why is this a binary decision? The final act will be to choose one of several. It's a multiple choice decision. Even when I go in to vote, although in this country it doesn't matter much, but in some countries it does, there can be more than one candidate, more than one way to vote. And many decision theorists involved in political science point out that our elections could be much more effective if in fact people were allowed to rate candidates instead of having all or none votes. So where we are forced into binary choices, it's often to very ill effect. As with medications, medication should be tuned to the patient. That's starting to be recognized in the PCORI movement. But it has been just about impossible to do that with many of the medical formulations that have been available, where they're just crude choices and pills that are unsplittable and other reasons, mode of delivery problems. We need to get away from binary thinking and forcing people into binary choices. So I don't see the world the way you described it.
Okay, fair enough. Maybe we'll come back to some more of that line of questioning in our Q&A. So thanks very much. If you could unshare your screen then for us, we'll move to our third speaker. That I'm very pleased to introduce us to Robert Matthews, a visiting professor in the Department of Mathematics at Aston University in Birmingham. Robert's a graduate in physics from Oxford University, and he's a fellow of the Royal Statistics Society and an editorial board member for Significance magazine. His publications on inference have dealt with issues ranging from barriers to the use of Bayesian methods in clinical research to the viability of earthquake forecasting. Robert has experience with science journalism, working for many publications, including The Times in London, where he became interested in the way a lot of research claims to be contradicted so often, and discovered that statisticians were concerned about this too. He's since moved out of journalism and now divides his time between consultancy and research into ways of making inference more robust. Robert?
Thank you very much, Dan, and thank you very much for inviting me to take part in this fascinating, very important, I think, debate about where next for this researchers. It's made back over years of about how inference is done, to see how we're getting on, how that's working out for us. And the fact of the matter is, as far as the progress of statisticians in changing behavior is going, it's not going at all well. Basically, your average research worker is still sticking with p-values and or confidence intervals. They still think the output of null hypothesis significance testing, p-values, is easy to interpret. And they want basically every study that they do, and also the editors of journals, want them to have a simple output that either the substantive hypothesis is either true or false. So it seems to me that what this is telling us is that the only way forward is a pragmatic one, and that is to basically accept all of the above, but with this change, that we need to make p-values and 95% confidence intervals more informative, less prone to misinterpretation, and also offer get them to offer more nuanced insight into what the data is actually telling us. So I think the way forward that is most suited to that, the framework that's most suited to that, to mean they have clear incorporation of weight of evidence through the likelihood ratio. They also have the power to extract more insight from data summaries like confidence intervals, and they also have a natural way through their through the incorporation of prior evidence of setting new things in context, which is crucial, particularly with implausible research. And as a journalist, I used to come across that sort of stuff all the time. So it's those last two values that I'm going to be particularly picking up on in explaining a framework that I've been working on over the last several years to try and develop a pragmatic way forward for working researchers. So it's called the analysis credibility, or ANCRED for short. There are a number of papers I've written on it, so I'll reference those at the end. And basically, it builds on the standard Bayesian approach of, you start with a prior, as everyone knows, you combine that with some function of the evidence that shows the weight of evidence that's been uncovered by the research, and you end up with a posterior probability. All very simple. Now, back in 1950, Jack Good, who's already been mentioned today by Sander, Jack Good, probably as a result of his work on code breaking at Bletchley Park during the war with Alan Turing, came up with this approach to dealing with the notorious problem with Bayesian techniques, which is setting the prior. And he said, well, why don't we just flip the problem around and say, okay, what would the prior level of evidence have to be for us to regard, when it's combined with the findings we've now got, for us to regard the evidence as now pretty compelling? In other words, what prior would be necessary for us to hold in order to view the new evidence that's emerged as credible at some confidence level, or credibility level in Bayesian? So in other words, we're reversing, it's sometimes called reverse Bayes, this basic approach. We're starting with the posterior of, yes, we want these results to be credible at 95% level, and then we are combining it with an inverse function of the evidence such that it allows us to work out what prior we need to already hold in order to be convinced by this new evidence that we're onto something. And that would allow us then to say, well, is this prior really credible? So instead of having to take somebody else's prior, elicited priors, for example, which is a notorious hang-up that a lot of people have got with Bayesian, each of us to decide, well, you know what, the evidence I've seen doesn't really work, doesn't convince me. And other people, they may already be convinced by the evidence that they've seen that, yeah, that prior is compatible with what I already know. So I think this is quite a compelling finding. So to make this operational and to go beyond very simple uses of this, we need to be able to sort of operationalize and be able to deduce that inverse function of the data. And so the way I do it is through the concept of find challenge of new claims that we read. So we start off with a 95% confidence interval, which is the summary statistic summing up the finding. And then we subject that evidence to a fair-minded challenge. Specifically, if the result is said to be statistically significant, then we challenge it by via the concept of a prior that represents a fair-minded skeptic of the substantive hypothesis. And then we ask ourselves, what level of skepticism is not seems to be statistically significant? With non-significant results, we do something very similar. We challenge by using a fair-minded advocate, a mathematical modelling of that. So what level of advocacy would make this result credible despite the fact it seems to be non-statistically significant? So let's have a look at the fair-minded skeptic. What does he or she actually look like? Well, here's that person. Basically, it's a skeptic in the sense that it's centered around no effect. The solution is centered about no effect, but the 95% tails are set by the strength of evidence. They're deduced from the findings we're now looking at. And they're also, as you can see, equally balanced. A fair-minded challenge. Now you'll notice there that there's a limit there. That's called the skepticism limit. And basically that's how the skeptic imposes his or her skepticism. Basically, unless the evidence is such that it lies beyond the skepticism limit, the skeptic can drag the new findings' weight of evidence back across the no effect line. In other words, the new evidence and the prior evidence combined end up producing a non-credible posterior. So we're looking to calculate that skepticism level for each new finding that we encounter using the stated 95% confidence interval that researchers use to sum up their findings. So with weak evidence, that's quite broad, and as you can see, the tail near no effect is, around about say 0.02 or so, quite just scraping under the 0.05 threshold. That's weak evidence, and the skeptic's response to it is that it's still it's the red dotted line there, and you can see that the skeptic is quite flat and quite broad, and the skepticism limit is quite large. In other words, the skeptic is going to need convincing of evidence beyond quite a high level, above quite a high effect size, before this pretty feeble evidence tips the skeptic over the edge into saying, well, I have to say, yeah, the posterior is now credible at the 95% level. So there's plenty of scope there for the skeptic to knock this weak evidence on the head. So with strong evidence, what we've got now is it's a tighter, because it's stronger, it's tighter. As you can see, the lower tail is quite a way away from the no effect line. And that forces the skeptic into a corner. The skepticism limit is much more restrictive, and that gives the person maybe much more scope for saying, well, there's already prior evidence for effects at least as big as this. So the skeptic is really pushed up against it by this strong evidence. Now, for non-significant results, we have the fair-minded advocate. So the advocacy is captured by the fact that the 95% tails just exclude no effect. So they are 95% confident, but the fair-mindedness of the advocate is expressed by the fact that the tails are bounded. He accepts that there can't be a limitless for him to be able to say, well, I still believe this non-statistically significant result. I still believe that's the maximum effect size that is still justifiable by an advocate of this effect in the face of this non-significance in the findings that have just been published. So doing the same as we did before, with weak evidence against a positive effect. And as you can see, the hump of the bulk of the evidence there is towards there being an effect. The tail area to the left of the no effect line is more than 0.05. Well, with that, then the advocate has quite a lot of scope. The advocacy level is quite high. In other words, the non-significance is so weak, it hasn't really pushed the advocate into much of a corner there. And it leaves the advocate lots of scope for dragging the new evidence across the no effect line into, yes, there's something happening here. On the other hand, if there's quite strong evidence against the effect, then the advocate is pushed into a corner and he's more restricted in his in what he can claim to believe anymore in the light of this evidence. So we have a 95% summary statistic of the finding, and then we put ANCRED into practice. We subjected to this fair significant result. We say what level of skepticism would make the result not credible. Non-significant results, what would make it credible. And then, now, if this was null hypothesis significance testing, you'd be faced with is the substantive hypothesis true or not? And that is replaced here by a discussion, which is, well, is that level of skepticism or advocacy justifiable? Where's your evidence? Cite it. How good is that evidence? And how does this new result constrain skeptics and advocates? So instead of being able to just claim, oh, it's more than 0.05, so there's nothing to see here, or it's less than 0.05, yeah, there's clearly something happening. No, you have to make a much better job, and much more effort at justifying your stance to be able to stand up your claims relative to the skepticism limit that's been worked out or the advocacy limit. So let's have a look at some examples. That's always the best way of understanding these things. So let's look at how ANCRED gets more out of significant findings. And a classic thing I was often faced with as a journalist is that really plausible? Great example of this was the Interphone study, a very large case control study, looking at the risk of brain tumours being caused by mobile phone use. Came out in 2010. It was huge. It's multinational. So it was a lot of interest in findings. And it basically found no overall gliomas with type of brain tumour risk, apart from for heavy users. Seemed to face a 40% greater risk of getting this type of brain cancer. And that was the 95% confidence. Oh, no, look, it's got a p-value of less than 0.05. Must be something in it. So a lot of people seized on that. But let's challenge this through fair-minded skepticism and say, well, what prior evidence is capable of making this statistically significant result not credible at the 95% level? So let's do that. So as you recall, that's the nature of the skeptical challenge that we're mounting here. There it is. And that range, the CPI in the middle, that's the range of values where if prior values then basically the skeptic has got you. He will drag that evidence of an effect back over the no effect line. So let's see how this works. when you operationalize the challenge criteria, you end up with this analytic expression for the size of the skepticism limit for ratios, and the U and the L are simply the upper and lower bounds on the confidence interval. So it was lower bound of 1.03, upper of 1.89, and that leads to a skepticism limit on the odds ratio of 2.0. So the result may be statistically significant, but it's only if there is prior evidence supporting at least a doubling in risk from the use of mobile phones. And there isn't any. It doesn't. At a biochemical level, an observational level, there's no evidence to back that up. So it might be statistically significant, but it isn't credible at the 95% level. So let's look at another problem. This one Sander will recognise because he actually published on this particular issue. This was to do with the possibility that statins taken for cholesterol may be protective against, yes, it's gliomas again, brain cancer. Now, there are good reasons for believing that from epidemiology and also lab evidence. And there were two studies to support it, and reasonably large studies. These were the two, and pretty consistent results, 25% thereabouts. A reduction in hazard ratio relative to not being exposed. So yeah, it's pretty good. Both statistically significant, near just about. But then this happened. This was published in 2016 rather, a failure to replicate. And it was very clear. Our findings do not support the previous sparse evidence, that's how they describe those two studies, about an inverse association between statins and glioma. And it was very, very large, 27,000 people involved. So let's challenge that. This is all a bit worrying. I mean, what's going on here? So those are the two previous studies. Oh, and here's Sudiger and oh, hang on a minute, that's a bit weird. The central value looks pretty close to what the other guys got. So what's going on here? Really? How did they reach that? And then, of course, you see that the upper bound of the confidence interval, so no effect, 1.17, so the p-value is greater than 0.05. So there we go. Well, let's have a look at this. Let's apply ANCRA, this time using the advocacy prior. There it is again. And for this time, the analytic result for calculating it for ratios from 95% confidence intervals is that we plug in the values and we find a advocacy level of 0.14. In other words, people who can point to evidence that there is a predictive effect, so all the way down to 0.14, anybody in that CPI, if they can point to evidence lying in that CPI, this so-called refutation falls over. And that's exactly what happens, because if you remember, those other studies were about 0.75, well in the middle of that CPI. So this so-called refutation, this so-called failure to replicate, is actually credible evidence for a protective effect within that bounds, and there is evidence. It's entirely consistent with the previous studies. And one thing that's worth noting here is never to be bamboozled by large sample sizes. It's 27,000, but the evidence is weak, and that's illustrated by the width of the confidence interval, and also the width of the CPI is which goes from 1 all the way down to 0.14. So don't be, ANCRA is warning you there about don't be bamboozled by large sample sizes. And finally, how to avoid over-interpretation of studies. This is a study that was published on, earlier this year on resuscitation techniques for patients who fall into septic shock. And basically it looks at two markers for how to basically treat the septic shock. One is capillary, I think it's reflux transfer. I forget what it's to do with capillaries in the body. And is that better than the standard, which is serum lactate levels, for dictating how to treat a particular patient? So Hernandez looked at this in JAMA in the randomized controlled trial called Andromeda Shock, and they found the mortality rate of CRT relative to serum lactate was a HR of 0.75, and that's good news. So it's clearly reduced the most supported, best supported value is for a hazard ratio of 0.75. That's really, really impressive. And the mortality risk difference, yeah, that's gone down as well by, yeah, not much, but, you know, we'll take it. That's pretty good as well. Oh, hang on. This is what they concluded, that CRT did not reduce all-cause mortality. Oh, what are we missing here? And of course, you look straight at the tails of those confidence intervals, and the odds ratio, the hazard ratio slips over the value of 1. The mortality risk difference slips over 0. So they're both statistically non-significant. So it's another one of those. But let's challenge that non-significance using fair-minded advocate prior, as before. This time for the hazard ratio, where it goes all the way down to the advocacy limit, all the way up to no effect. We plug in Hernandez's findings, 0.55, 1.02 with the bounds, and we find the advocacy level goes all the way from there may be a tiny protective effect, all the way down to a massive protective effect, because the AL level is so low. Basically, that whole field is all taken up. Anything in that huge range constitutes evidence for a protective effect. It's so-called non-significant null support for the CRT approach actually provides credible evidence of a protective effect if basically you've got any prior support for one at all. And there is quite a lot already. What this is really showing you is that this study is just very, very small. In fact, the researchers said they had to self-fund it to get as many as they did. So, you know, they had to set the power to reach a pretty high degree of impact, and basically they couldn't do it. They lacked the power, and ANCRED is reflecting that by saying it's really the advocates down at all. It's not really changed what we think at all. But those central values in the confidence, the point estimates in the confidence interval is very encouraging, and bigger studies are clearly merited. Now, there's something interesting here, and there's a wider point that I hope people will want to debate, and that is there was some to and fro on Frank Harrell's data discussions forum about this, saying, oh, here we go again, the researchers, you know, mangling the use of confidence intervals and saying, oh, look, it's just slipped over, no effect. So, you know, there's nothing at all to see here. Turns out that the authors did not want to focus solely on that non-significance. And they said in interaction with the forum that we actually think that CRT is better than lactate. And you can understand why, because the point estimate for that confidence interval was, you know, a long way south of no effect. It was really quite impressive. But here's the thing. The reviewers and editor asked us to temper our enthusiasm and stick to the cold stats. That's what one of the researchers said. And we all know what they mean by cold stats. We're talking null hypothesis significance testing, and we're talking about, is it less than 0.05? And you've got to go with that, because if it's more than 0.05, there's nothing to see here. And what ANCRED does is to give researchers extra scope in the form of a quantitative alternative to this ludicrous pass-fail dichotomy that is so often used and so often mangled in so much research we see today. So, in conclusion, I think ANCRED, I could make the claim that it's a small step in the sense that it doesn't require, you know, massive investment in, you know, understanding Bayesian techniques. It boils down to a few formulas, and it uses conventional, widely used and accepted data summaries. It extracts more from summary statistics. And it also helps promote the publication of non-statistically significant null results. Because it rescues a lot of them, saying, well, it might be non-significant, but all it does is put the advocates of an effect in a bit of a tighter corner. And you can actually quantify how tight a corner they've been put into by the new evidence. It highlights weak evidence from large studies, stops us being fooled by that, and it replaces dichotomy with contextual debate. The level of prior evidence we need to have to be able to stand up a finding. I'm developing, along with some others, ANCRED further. So we're looking at out of the blue with Bayes, because if they're out of the blue, it's very difficult to know what the relevant prior is. So I came up with this concept called intrinsic credibility, which Leo held at the University of Zurich, is now expanding, with very interesting results for the concept of the 0.205 threshold. He has found, using the concept of intrinsic credibility, a principled way of arriving at that 0.205 threshold. Replication probabilities, again, the reverse Bayes technique, Leo at University of Zurich is expanding on that. And we're also looking at moving beyond normal distributions and inferences on differences in ratios. And while we're working on this, you guys out there, you might want to use ANCRED to look at some of these classic issues that come up time and time again, because you might find that applying the ANCRED methods allow you to make more sense of these. And you might just want to take some of your own pet concerns about certain studies, apply ANCRED to them, and they might just give you a new perspective on them. So thank you very much. And here are the references.
Thank you very much, Robert, for that talk. I wanted to comment that I came across a paper by Wagon Makers, I don't remember where he talked about the Fisher-Jeffreys conjecture. And I didn't know about this conjecture until I read it there, but apparently during 1934 and 1937, Fisher and Jeffrey challenged each other with statistical puzzles to challenge each other's way of thinking. And I found Jeffrey's summary of those exercises really interesting, and I wanted to get your thoughts about it. Jeffrey says that these activities confirm my previous impression that it would only be once in a blue moon that we would disagree about the inference to be drawn in any particular case. And in that case, we would both. I felt like that's kind of related to your proposal to look at a problem in two different ways here, Bayesian frequentist, and see when you would be in this zone where you really feel uncomfortable with the decision in one or the other camps.
Yeah, well, yeah, the problem with drawing lessons from that is that Fisher and Jeffreys were both very accomplished statisticians who were able to use quite nuanced techniques. The reasons that there is such violent disagreement likely to emerge if you use ANCRED is that so much of the debate, as we see in papers at the moment, is basically the result of turning handles on sausage machines and saying, but it's greater than 0.05. It's game over. There's nothing to see here. I'll tell you what, we're not even going to publish it. It's pointless because the referees, the editors would not be interested. Or on the other side, hey guys, yeah, I know it's nonsense. I know it's homeopathic, but it's got a p-value of 0.045. We've got something here. We can publish it. And so it's we are nowhere near getting the sort of level of sophistication in debate that Fisher and Jeffreys were involved in back in the day, in the 20s and 30s, when these things were coming out. And Jeffreys was the first person to criticize Fisher and what was in Statistical Methods for Research Workers, which is the book that really started the rot, where basically Fisher just handed over a set of rules and formulas without including the proofs and said, yeah, guys, if you're working in a lab, this is what you need. Okay, that's it. That's statistics done for you. If you need to speak to a statistician, try and do it at the beginning. Other than that, this is all you need to get your work published. And that's where we are now, and we haven't moved on in 80 years, and that needs to change. And I hope that ANCRED might be a step towards that.
Okay, thank you. If you could stop sharing your screen, Robert, and I'd like to invite Sander and Jim to join back into the panel for our question and answer discussions. I have a few questions I've been formulating and collecting. I wanted to start with going back to Jim about the cutoff, and because you're kind of now proposing maybe two cutoffs, one with a suggestive kind of interpretation and one not. So I don't know, we've heard from Sander and Robert about some caution with dichotomous thinking, but I still feel myself wanting to make it a yes-no or a go-no-go decision. So I'm kind of still thinking that I might need cutoffs, but I also am remembering Robert Rosenthal's comment about surely God loves the 0.06 as much as the 0.05. So I just wanted to get your reaction to cutoffs and Robert Rosenthal's comment. What do you have to say about this?
So I would, instinctively be opposed to cutoffs myself. Unless they're in like this GWAS situation where what's the feedback coming from?
Robert, could you mute? Yeah, thank you.
Okay. Except in scenarios like the GWAS situation where the cutoff was scientifically determined, and it was done just so that it can be used by scientists in future GWAS studies, which the same kind of experiment, the same kind of thing is being done. So having a cutoff there, just making the scientist's life easier, I think is reasonable. The 0.05 and 0.005, well, Robert pointed out that the scientific culture is not changing fast. And so I think we're stuck with cutoffs for quite a while. And I would just rather the cutoff be 0.005 than 0.05. Mm-hmm. We're stuck with them.
Okay. All right. Thank you for that. I'd like to go to Sander. And one of the other things that I caught from your comments, you mentioned that publishing research based on the quality of execution of a study and not on the results, something to that effect. But is that sort of hinting toward not using inferential methods in presenting an analysis of the data?
No, it's simply a proposal that's been around for quite a while now to say that studies should be considered for publication based on report of their methods and perhaps descriptive elements of their data and nothing more. Once they're accepted based on the quality, then they are now presented with the results of the analyses, whatever those might be. In other words, there's a clear selection bias created by choosing to publish studies and publicize them and emphasize results based on their statistical results. We want to see those results. We don't want them censored in some fashion where we have to guess what was missing, what studies weren't published. And that's the whole issue.
Yeah. In fact, now that you've clarified what you mean by that, there is I can distinctly remember a paper in the special issue of the American Statistician that talks about it. I think they call it like an open science publication model or something like that.
Oh, just a footnote. I think that quote about God loving 0.06 as much as 0.05 might have originated with Neyman-Pearson way before.
Okay. Yeah.
But maybe they didn't know that.
Right. Okay. Robert, I'd like to come to you. And I've been reading lately about this method called ROPE, Region of Practical Equivalence. And also there's a paper in the special issue pertaining to second generation p-values. And there's some similarities, I think, between ROPE and second generation p-values. They both kind of work like this, where you, and I think Sander will appreciate this part of it because it stipulates in the beginning that you have an interval null hypothesis. And you have that interval null hypothesis to say that anything in this interval is going to be basically what is no effect, right? And then the idea in either ROPE or second generation p-values is you come up with some kind of interval. And in ROPE, it's a Bayesian credibility interval, and in second generation p-value, it could be a frequency interval. And you look for the intersection of your interval with the null interval. And it's very intuitive that if your Bayesian credibility interval or your frequent risk confidence interval lies completely within the null interval, you might accept the null. And if it lies completely outside, you might reject the null. The part maybe that's a little bit not so intuitive is that if there's any sort of overlap at all, you don't make a decision. Maybe that's not a bad thing. So I just want, maybe we can ask all three of you to comment on a procedure of that type. What sense does that make to you?
Well, for me, it makes complete sense. I should point out that this idea of testing intervals with importance, goes back at least as far back as Hodges and Lemon, 1954, and it reappeared in the literature many times since in bioequivalence and equivalence testing. There's even whole books that are discussing that. There's one by a German author, Bellick, that discusses that. So these are being rediscovered. That's a good thing. But I think that from the square one, we should have been talking about testing intervals and talking about laying out what's important effects and what's not. Not intervals that we call null, but intervals of we would accept as if the effect's in there, that we're going to act as if there's no effect or close to no effect, negligible effect.
Now, Sander, can I point out one thing, though, that I'd love to hear your comment on this, because if you like interval nulls, and I do too, the critics are going to say, well, how do you come up with that binary decision about when the interval should stop, right? Let's say the null interval is A to B, right? So choosing A and choosing B is sort of a binary decision, isn't it?
Guess what? Statisticians can't answer that question any more than they should be answering what alpha should be. It's contextual. What's the context? What's the cost of the errors? Is the cost getting a cold, or is the cost dying of cancer? All those things need to be considered about how you weight these things, where you put those intervals. What does a 50% increase risk mean? Does it mean a 50% increase in risk of dying on the operating table, or a 50% increase of risk of feeling bad for a day from a shock?
Well, I absolutely agree that context is everything in deciding A and B, but even then, you have to decide what is A and what is B, right?
But again, it's not within the realm of statistical theory, except to say, here's where we have to have essential input from the context. There are no universal rules, and the use of universal rules will create grotesque distortions in the literature and reporting, as we've seen in examples from JAMA, which, by the way, I think their editorial policies of JAMA have reached a criminal level. I am not afraid to say that.
Totally agree, but not agree more.
It's criminal what they're doing. Misreporting results and ignoring their state-of-the-art statistics 1950, although I don't even think Neyman would have condoned it. And it's
if I ever want test cases for ANCHOR, I just look at the latest issue of JAMA. I can always find one or two.
Yes.
Jim, what do you think about these intersection kind of interval procedures? Do they make sense to you?
Yeah, they make sense. I mean, it's sort of any Bayesian analysis of a reasonable problem makes sense to me. The one thing I would comment upon is the notion, though, that everything should be an interval. Like in the GWAS example I was talking about, there the null of no effect between gene 389 and brain cancer. The null of no effect there is quite plausible. I mean, there may be just an epsilon effect or something, and you might want to say it that way, but mathematically there's no difference between saying there's an infinitesimal epsilon effect and zero effect. Mathematically, for the sample sizes they deal with in those studies, you can assume that all of those nulls are point nulls, zero effect, and you'll get the same answer as if you had chosen some teeny little interval somehow.
Mm-hmm.
So I mean, the notion that all testing has to be intervals, I think, is wrong, because the point nulls are a useful simplification that applies in most of the testing scenarios I deal with these days. Not all, but most.
Yeah, I'm thinking.
Well, I was just going to say, conversely, in most of the scenarios I deal with, they're not credible. Although I think point nulls are useful. They're very useful. In fact, they can be used to help build up interval hypotheses. We can talk about a lot of the equivalence procedures are based on testing the endpoints of the interval with as if it were a point null or a boundary and a one-sided test. So we're just talking about use of tools, but proper use of tools. There's a place for all these tools somewhere. They're just no such thing as a universal tool. A screwdriver will not drive nails. A wrench will not drive screws.
Yeah, so sticking with you there, Sandra, sometimes I wasn't clear like what you would want us to be teaching our students in terms of the proper way to handle a collaboration, let's say with a plant scientist who wants to know if treating the plant with this type of regimen is going to increase its resistance to disease. So they do an experiment, maybe a longitudinal study. They want to decide, did the treatment have an effect? I wasn't entirely clear what you would want us to tell our students to do to help them with their data analysis. What would you do in that situation?
Well, it's interesting you put it that way, help them with their data analysis. I would say, I would ask, how about designing a research program, perhaps a series of experiments to explore this, which could be stopped at any time. But well, I want you to understand, I'm not an expert in plant science or any of those contexts where these sciences, like psychological science, where they do a lot of small experiments. A whole program sometimes is presented within a paper, like in neuroscience, a series of experiments to explore a topic. Whereas I deal with an area that is along the line of what Robert was discussing, observational studies of side effects of medical device, post-marketing surveillance of drugs, where what we have are large databases, and the serious concern is about biases, not about random error. Most we can be talking about what kind of associations do we see in this situation with many unknown biases. So I deal with and have taught in a very different topic area. But what I would start with all these things, I'd say we need to talk about the psychology of inference from square one before we even talk about such esoteric things as p-values. We need to talk about how people's biases will influence what they see and what they want to conclude, and how the problems of integrity, and how people will be tempted to cheat and maybe p-hack in one way or the other, depending on whether they want to see an effect or no effect. Those kinds of things, I believe, should be covered up front at the start. That's statistics one, that separates it from mathematics. The statistics has been too obsessed with focusing on the mathematics, the computation, and not paying attention to the scientific context. That's fine to call that mathematical statistics, but it is not fine to call that applied statistics or statistical science or statistics for science.
Yeah, I think that's one of the advantages of the open science movement, where they require that you say how you're going to do the study first, and so it's possible to check whether issues like bias and confounding have been adequately dealt with in the study design, because once they're in the design, they're the devil's own job to extract from the findings. It's where the focus is always on the effective play of chance. If we can deal with the really tricky stuff, it's hard to quantify bias and confounding through appropriate experimental design before the study is even done. That's got to be an improvement.
Okay. Jim, I wanted to come back to you because you mentioned some caution using Bayes factors with non-informative priors. So if I wanted to do a Bayesian analysis with even improper non-informative, should I avoid using the Bayes factors? Jim, we're not hearing you.
Now? Okay.
Yeah.
For some testing problems, it is okay to use those priors, but for the type that I was talking about today, like testing state equals 0, you can't use vague proper priors. So you do one of two things. There are what are called conventional priors for testing that are just like automatic off the shelf. You can use it, or you do the robust kind of analyses that I was talking about, where you look at bounds over classes of priors. So you try to make statements that are true for a quite general class of priors.
Mm-hmm. One of our viewers wrote in and asked about the default priors that are often used in psychology experimental data analysis. I don't know if any of our speakers are familiar with what those priors might be. Does anyone have a comment on?
You mentioned somebody mentioned E.J. Wagenmacher, and he and his group have prepared. They have a computer package going that's Bayesian, and they use these default testing priors that I talked about earlier. That they were originally developed by Harold Jeffries, that we talked about, Arnold Zellner, and others. So they exist. I mean, they're if you don't want to go to the trouble of developing your own prior, these things exist.
Okay. And another viewer wrote in, this is a question for all of you. The viewer said that the discussion is reinforcing my proposition that federally funded science needs to be replicated by an unfriendly group or lab before it's allowed to be published. Is this a good idea? Sandra, you want to start us?
Well, I think it sounds absurd to me. I want to see all the data. I want to see what everybody's done. Well, I don't know where this is coming from, but allowed to be published. If somebody did a study, somebody has data, it should be out there. I don't care what the p-value is or what the hazard ratio is or the confidence interval is. I don't care if it's a tiny study with a huge confidence interval. It's a piece of information. I want to see it in the entire database available to the people who are going to synthesize and summarize this evidence. This kind of selective censoring that's taking place is the major source of problems today in so many literatures, including medicine.
I think maybe where the viewer was going was to avoid the impulsive reaction that we're all getting whiplash from the latest study that shows chocolate is good for us and it's never replicated, right? So in that, looking at it from that lens, do you still feel the way you stated?
Yeah, it has to do with the fact that most of what I see is non-replication is just misinterpretation. It's what Robert showed in his talk with the statins and glioma example. They claim this study was not replicated, there's whiplash. You go back, every time I go back and look at the original studies, it's almost never do I find any genuine conflict among the results. All I find is that the studies were misinterpreted. Sometimes the first ones are misinterpreted as being surely positive because they got p greater than less than 0.05, and then they were said to be not replicated because they got p greater than 0.05 in the next study or a later study. And in fact, you look at the two of them, and as in that example, they're right on top of each other. The only difference is their variances. It's really appalling what's out there, and it makes you appreciate Tversky's comment that we are all stupid. These are supposed to be trained scientists with massive federal funding, but the skeptics, and I call them pseudo-skeptics, to believe in the null is not skepticism, it's just adopting a certain biased position. To be an advocate for an alternative is another biased position. What is real skepticism? It's basically, I would call it not believing any of these people and not believing these statistics, looking at the evidence for yourself, and then realizing that a lot of the evidence has been censored from us. It's hidden. Pharmaceutical companies will hide a lot of negative results on product development because they want their competition to go up the same blind alley. And then, of course, there are journals, many big ones, that won't or will look poorly on a non-significant result. And this creates a bias in what we're seeing. And what we're seeing doesn't look good at all, even if there were no publication bias.
So Jim and Robert, we're really kind of talking about the reproducibility crisis, I think. And what do you have comments about how you're
I was recently looking into applying ANCRA to these particular issues. And I was particularly struck by the historic case of streptokinase, where I think it was the first 6 randomized controlled trials, all of them null, absolutely all of them, year after year. And it took like 5 years for any single study to demonstrate efficacy in the normal way, i.e. to have a statistically significant result. But what actually happened is, to Sanders' point, all those piffling little studies, they all managed to get published. And then Antman et al., in a very famous paper, did a cumulative meta-analysis, totting up the evidence as it accumulated. Around about the third of those hopelessly null studies, there was cumulatively an effect. But if you took them all in isolation, there was nothing at all until about the sixth or seventh of these tiny studies. And that's why with replication, we've got to be really careful about, if we do a replication that fails, automatically, well, that's it. The thing hasn't stood up. We can forget the whole thing. It's got to be cumulative again with replications. We've got to accumulate replications as well. They're not sort of single bullet to the head type refutation, which is, I have a bad feeling that some of them are being seen to be.
Yeah, and one proposal has been that if somebody presents a new study, supposedly a replication that they present, first of all, they present a direct statistical comparison, perhaps a p-value even, for their study versus some summary of past studies to see if there really is some distinction, and then present a summary estimate from all the studies, including theirs, as part of their discussion. In other words, they have to do at least a mini meta-analysis before they start claiming they failed to replicate or anything like that.
Yeah.
But it all comes down to user problems in this fashion that we've described. And I attribute those problems much more to us, our teaching, than to the users who are simply at the mercy of a system that is demanding things like the less than 0.05 to publish.
Okay. Jim, do you want to offer anything on this topic before we come to
well, just in terms of your original question about mandating replication, I think, if there's an important result out there, people will try to replicate it. If it's just one of these nonsense results like chocolate affecting blah, 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 nobody's going to bother to waste the money to replicate it. So I think science does a good job of figuring out what to replicate and what not to.
Okay, all right. So we are winding down to the end of the webinar, and maybe a nice way to close it up would be to offer each of you a chance to leave us with maybe an uplifting thought or some other thought that you want us to take away. So let's start with Jim.
Okay, so I did not at all focus on what I would like to see the world be. I think, as Robert pointed out, even after the uproar of the last few years about this p-value issue, nothing much seems to be changing. So with that in mind, I was just trying to propose 3 simple things that can be done and implemented immediately that I think improve the situation. They're not the solution, but they are a big improvement. So I would just encourage everyone to adopt them.
Okay, very good. Sander, a couple of comments to close up your remarks.
Well, as I said, I wanted to try and bring up one of my slides. So what do I hit share here again, and then go, and then hit in closing. And you can see that slide. So this is my closing remarks, that blind acceptance of mathematical frameworks, deification of great men and their conceptual errors, and neglect of cognitive problems have rotted the core of statistical training and research practice. That's not uplifting. The replication crisis, hysteria continues the problem via its nullism and dichotomania. And I say we must rebuild statistics as an information science, not a branch of probability theory, with cognitive science as a core component. Probability theory is an important mathematical tool in all of the statistics, but it's just part of it. It's just a tool, and it has sort of eaten up the whole of thinking and so much of the concentrated thinking and thinking about these problems, when in fact, I think that the evidence from empirical evidence from the literature of how people are misusing statistics and how it's distorting literature shows that a key component of statistics has to be cognitive science, or whether you want to call it psychological science. That's a hard pill to swallow, because that's going to make statistics much more an experimental science about classroom experiments in seeing what works, and then literature experiments about seeing what works. So there's a long road ahead of us, in part because we have not been empirically grounded enough in our theory.
Okay, well, thank you. If you could stop your share, and then Robert, how about a final word?
Yeah, my final word would really be a call to arms to the statistics community. I mean, Sanders blames us, in the statistics community for not doing more. I think the people to blame here are not the users of these techniques either. In other words, research workers. They will do whatever the journals, especially the influential journals, want them to do. These journals, and we've already, Sandra and I have already mentioned JAMA, and there are many others. They just have to be called out by the statistics community as a whole. We need to get heavy with these people and really draw the attention of the public and maybe, you know, governments to the fact that they are the main conduit driving inadequate inference and misleading science across the board.
All right, well, I admire all of you for the passion that you bring to this topic and certainly your accomplishments in our field. And it's been a wonderful honor for you to be in our webinar, and it's been a lot of fun. So I thank you.
Thank you
for that.
Thank you very much. It's been huge fun.
And thank you all viewers for tuning in. I'm sure you'll hear about another upcoming webinar from NISS soon. Have a good rest of the day.
Thank you.